All right, in our next assignment, we're going to be looking at something called torque and making some calculations and building an Onshape project to meet certain torque requirements. And the first thing we want to consider is, let's imagine there's a C channel here, and at the end of the C channel is a mass of 5 kilograms. And we'll imagine another C channel down here, double the length, also with a mass at the end of it of 5 kilograms. And if we imagine that there's a motor over here, call that motor, and we'll put a motor on this one as well. And the motor is going to turn, and the C channel is attached to the motor, and we'll rotate our mass up. So in order to do this, the motor has to supply a certain amount of torque, T-O-R-Q-U-E, and you can think about torque as rotational force, in order to lift the object or swing it up above the motor. The distance that the object is away from the motor or from the point of rotation is going to affect how much torque is required. And you should think out loud to yourself right now, like, which is going to require more torque, a greater distance or a smaller distance? If you'd like to check that yourself really quick, there's a real simple demo you can do where if you take, say, a glass of water or something like that, something heavy, and you hold it straight out and then raise it so that your point of rotation is your shoulder, and you could feel like, well, how much torque force is required to do this kind of maneuver, but then bring it in tight to you, change the pivot point down to your elbow, and now rotate it here, and you should find that that's significantly easier than when you're out here. It's not a perfect example, of course, because you have different muscles in different areas, but you should get the idea. All right, so if we want to calculate torque, torque is going to equal the distance the object is away from the point of rotation times, and that's in meters, times the force or the weight of the object, basically, in newtons. Newtons may be a new unit for some. It is abbreviated just with a capital N. So distance is pretty straightforward. We could, for example, say, oh, this is 1 meter and this is 2 meters, and we know what that is. And if it were in inches, we could change it to meters, etc. But force, we're going to have to make some calculations. Once we know kilograms, it's pretty straightforward to convert to newtons. So if we want to go kilograms to newtons, we take our kilograms, in this case it's 5 kilograms, and we multiply it by acceleration due to gravity. There I am, right, little g, which is 9.8 meters per second squared. And 49 kilograms times meters over second squared. Kilograms times meters over second squared. And kilograms times meters over second squared, we also just refer to as a newton, so 49 newtons. Okay, and that's the force, that's the weight of the object, and that's how much force is required to move the object basically in any direction. You're going to need 49 newtons of force. Okay, so now if we consider this, excuse me, episode A, this is episode B, and we say let's calculate the force required for A, it would be torque is going to equal 1 meter times 49 newtons, or 49 newton meters. And in B, torque is going to equal 2 meters times 49 newtons, or 98 newton meters. So if we double that distance, we're going to double the torque force that's required. So we've determined, if we just look at this first scenario up here, that in order to take this 5 kilogram mass at 1 meter away from the motor and actually rotate it, we are going to need to provide 49 newton meters of torque to do that. So how do we determine how much torque is available, and how do we get the 49? Well, for one, you've got to look at your motor that you're dealing with and see what its torque stall value is. So for the Vex green motors, VEX, and the green is the insert gearing that's in there, there's a torque stall equal to 1.05 Newton meters. That's the point where it will not be able to lift anymore. So we have a motor that provides 1.05 Newton meters of torque, and we need to be able to lift with 49 Newton meters of torque. I mean, we're very far away, but it can be done by using gears. So when we're thinking about gears, and we need to be able to consider gear ratios, and we did a little bit of that in Onshape, but your gear ratio can be determined in a couple ways, but an easy way to do it is just look at teeth in the output gear divided by teeth on the input gear. So in other words, if I have a 12-tooth gear and it's hooked up to an 84-tooth gear, and I want to figure out my gear ratio, I'd say, well, teeth on the output is 84 divided by teeth on the input is 12, and I'd have a gear ratio of 7. Another way to determine the gear ratio, I'm just going to write it down here, is to take the torque provided by the output and divide it by the torque of your input. Again, your input is like where the motor is connected. That would be in this case. So if I know what my torque input is, because we listed it here, it was 1.05 Newton meters, we can solve for torque on the output by just saying torque output over torque input equals that gear ratio of 7, and torque input we know is 1.05. So we can rearrange the equation to say torque output over 1.05 Newton meters, that's the given torque stall by VEX on their motor, equals our gear ratio of 7. If we cross multiply, we'll get torque output equals 7.35 Newton meters. Now, we didn't quite get to the 49 Newton meters that we're going to require, so we're going to need to do some more gearing to get there. And this is a great time to introduce what's called a compound gear. So if you place two different size gears on the same shaft or axle, refer to that as a compound gear. And now I've got another 12 tooth that's sitting on the same shaft as this 84. And if I were to come in with another 84 tooth gear, I'm just going to put something underneath it to support it. Stay there. Now we can look at, all right, well, we've done it again. We've got another 12 to another 84. We're going to get another magnification of our torque by a factor of 7. And you might just think, well, this is 7 times, and then this is another 7 times, and 7 times 7 is 49. If you want to think about it from how would you calculate it? Again, if you say, here's my gear ratio when I'm dealing with multiple gears, it's still going to be teeth on the output over teeth on the input. But then you would just say times the next one, teeth on the output times teeth on the input. And in this case, that would be 84 times 84 over 12 times 12, which equals 49 for a gear ratio. And if we took this gear ratio and we subbed it right in there in the last equation, we'd have 49 times 1.05 Newton meters, which would give us 51.45 Newton meters of torque force in order that would help us lift and get the object up, which accomplishes and matches our 49 Newton meters that we were trying to get. So we could use this kind of gearing situation to lift up that object, that 5 kilogram mass. Now there's one more part to this that makes it a little bit more confusing, but it's reality. And that is that every time you have one gear interfacing with another gear, you're going to have some friction of the shafts spinning through the C channels, through the bearing flats. There'll be friction between the teeth, and some of the energy is going to be lost in the form of heat. And in general, we say that the loss due to friction between one gear and the other is about 10%. And that's from a power perspective. We're losing 10% of power with each different transition. And we can also consider that with each transition, we're losing about 10% of that torque increase. So if I go back to my 51.45 and say, hey, I was able to gain a lot of torque by doing this gearing system, but I lost about 10% and another 10%. I lost 20% of that gain in the process. So if I really want to know how much torque is going to be available to do the work for me out here, I've got to multiply it by 0.8, right? Because 10%, 10% is 20. That's the amount of output I'm losing. The amount I'm going to get is 80% of this number. But we were so close. And we're still not at 49. Now we're back at 41 due to some losses due to heat. So what can we do? Well, we can add more gears. So in my case here, I'm going to take a 36 tooth gear at this point, and I'm going to attach it to a 60 tooth gear. So one last time. So now if we go back to a fresh blank piece of paper here for a moment, and we say, all right, what is our current gear ratio that we've established? And again, that's going to be teeth on the output divided by teeth on the input. So if we're looking at, because we have a lot of things going on here now, right? This is an output gear, and that's an output gear, and so is that. So we've got 84 times 84 times 60. Coming back to my paper here. 84 times 84 times 60 on my output, and my input, I've got a 12, a 12, and a 36. So 12 times 12 times 36. And if we do all that math, we get a number of 81.7 as our gear ratio. And we'll do the same thing we did before. 81.7 equals torque of the output divided by torque on the input, which we know is 1.05 Newton meters. We'll get 85.8 Newton meters on our output. Sorry, put that in there. But don't forget, we also have to deal with this efficiency problem. And now we've got an extra set of gears. So now we lost 10% in going from here to here, another 10% going here to here, and another 10% going there to there. So we've really 70%, because we lost 30% of it now due to heat. We're only going to really have 70% of that number. So I'm going to multiply that whole thing by 0.7, which will give me 60, call it 0.1 Newton meters. And with that value, I'm definitely significantly bigger than 49. And I can feel confident at this point that if I were to set up that gear ratio, I would indeed be able to lift up that 5 kilogram mass at a 1 meter distance. In this next assignment, you're given an 8 kilogram mass at the end of a C channel that has a distance of approximately 0.40 meters. And you are to design on Onshape a lifting mechanism, a very simple one, that can actually move this and lift it. Mechanism. There are a couple things I want to see. Get a C channel in place and fix it to the origin. Attach a motor. And it's not necessary that you put all the bearing flats in, but you can see what I did here. I have a 12-tooth gear going to an 84, and then I made it a compound gear by putting another 12 on this and running it to another 84, And you could see I just kind of quickly haphazardly put a C channel on there. And that distance should be approximately, if I assume there's a mass at the end of it. If you want to check distances on things, you could just click anywhere on here. So pick a point and then go to another point. And for example, that says 15.596 inches. I'd have to do a little check on that to see what that is in meters. There's a way to switch it, but it should be close to the 40 centimeters if you use a full size 35 C channel. And put the gear relations in place properly so that if you were to animate, let's see, Revolut 1, we can see this working ever so slowly. Barely looks like it's lifting. And in case you haven't figured this out, if you want to make things go faster, you can change the number of steps and the end value. So say I only want to go for about 90 degrees, and I'll change my steps to 100. Then I'm going to hit play. Boy, it still goes even really slow. I'm going to change steps down to like 25. And that goes a little better. So it's interesting. It's only going from 0 to 90. Oh, because it's doing 0 to 90 on this. All right, pause on that. So make this like 360 on this one and hit play. And that looks a lot better. So you don't have to go crazy with it, but I do want to see the gear relations. I want to see the gears you put in place. I want to see that you use compound gears and you have a C channel on there that will allow you to lift that 8 kilogram mass. So you're going to have to make sure the gearing can get that job done. You don't have to gear it the same way I did. You can gear it any way you would like to. Best of luck.